All right, guys, today we're going to introduce the pH scale. A lot of you guys have some familiarity with the pH scale, and as you might know, the pH scale is a scale that we use in order to measure the acidity, or you could even say the basicity, remember acid base, of a solution. A lot of you guys might already know that the pH scale ranges from a 0 to 14. So you guys want to copy this down. I don't know if you guys can see it, but you'll notice right here, smack dab in the center, it's a neutral is a 7. Something that has a pH. If you had a solution that has a pH of 7, that would be neutral. And anything that has a pH lower than 7 is acidic. Okay, and anything that has a pH greater than 7 is what we'd say basic. So the lower the pH, the more acidic. The higher the pH, the more basic. So I have some different naturally occurring substances covered, just to kind of give us some time to maybe think about what might have a certain pH. So I kind of want you guys to think natural, from a natural in the natural world, because we can have acids and bases highly concentrated within a chemistry lab that actually could exceed this pH scale. So we want to think about naturally occurring substances. So the substance that you can think that would be the most acidic, and I know what maybe some of you guys are thinking, maybe you guys are thinking maybe like a lemon or something like that. You guys remember acids are sour, but there is some that would be more acidic. And if I told you it was on your body, you guys think about it, what should you be thinking? You're probably thinking your stomach. You guys should know you have stomach acid. In fact, stomach acid is actually hydrochloric acid, HCl. So I know that looks kind of funky, but that's just a stomach. So that would actually have, your stomach acid actually has about a pH of 1, okay? So then, as we move this way, we're going to get we're getting less acidic. So what might be less acidic than stomach acid? And you guys guessed it correctly. We have lemons. Lemons would have a pH of about 2. And you know what? You can put oranges there. Remember I had said before, oranges are probably just as acidic as the lemons. The reason why they don't taste as sour is simply they have more sugar. Something that's less acidic than lemons, yet acidic nonetheless, are grapes. And I don't know if you guys have ever had sour grapes. You know what grapes, when they're not ripe, they taste really sour. And you guys know why that is, because if you pick them too early, they haven't had enough time to mature, enough time to create enough sugars to counteract that. But when the sugars are absent, you can definitely taste the sourness of grapes, indicating that they're probably acidic. The next one, you guys, this is actually the one that disturbs me the most, because when people suffer from acid indigestion or stomach ulcers, for example, like maybe you have grandparents or something have stomach ulcers, and the problem with that is like the inside lining of your stomach, which kind of protects it from the acid, it starts getting eaten away, and therefore when your body's producing acid when it's eating foods, now that acid is doing some further damage to the inside of the stomach, and it's quite a painful experience. If you were to go into the doctor with stomach ulcers, your doctor's going to tell you to stay away from this kind of food, which has about a pH of 4. And this is kind of hard for me, because this food is tomatoes. You guys think about all the foods you eat with tomatoes, especially if you like Italian food, lasagna, spaghetti, and pizza. You probably have to put that on the back burner. All right. So you notice, we're becoming less and less acidic as we move up in pH values. What's slightly less acidic than tomatoes are bananas. And then what's less acidic than banana is actually milk. You know how you get milk? Because milk, you guys know, right? If you're working out, you want to have milk because it has some protein in it. And then you guys think about, from biology, the basic building block of proteins are amino acids. So therefore, it shouldn't be surprising that milk would be slightly acidic. And when you guys are thinking pH 7, something that's neutral, probably the first thing that would come to mind, is just pure water. Okay. And then now, notice now, you guys, now this marks a change. Now anything above this, now it's no longer acidic, but it is basic. And so something that's really, that's slightly basic, might be kind of surprising, would be eggs. Eggs are slightly basic. And then you guys, that's it on food. Something that's more basic than eggs, think about something that you might have in your refrigerator, right, to kill odors. We can use it in cooking. Baking soda. Baking soda is called sodium bicarbonate. That is, and you remember I said that when we have an acid spill in the classroom, prior to cleaning it up, we would try to neutralize it with a base. In this case, we have some baking soda that we have in the classroom that we pour on the acid before we cleaned it up. What's more basic than that? You guys remember we talked about this in that first unit. Soap. Soap is basic. And then what's more basic than that is, think about a cleaner that you often use. In fact, you guys, what you'll find is a lot of cleaning detergents and such are on the basic end. And I know it's hard to see, guys, but this is showing a bottle of ammonia. Ammonia might be something that you would use at home to clean. Think about Windex. You guys, Windex is essentially an ammonia solution. Ammonia is NH3, which is dissolved in water to make ammonia solution, and then they add some blue food coloring, and then they call it Windex. That's essentially what that is. And then the most basic thing that you might come in contact with is oven cleaner. Oven cleaner is NaOH, sodium hydroxide. Think about, you know, how nasty your oven can get after you've been cooking things. You need a really strong reactive substance. What often we use is oven cleaner. Okay, so you guys, this is kind of a range of somewhat naturally occurring substances from a pH range of 0 to 14. Okay, now I want you guys to also put down, so think about it. Okay, this, so rewrite your pH scale. Okay, you guys remember your pH scale is 0 to 14. Now you guys, these numbers correspond to something, right? It's not like when somebody developed the pH scale, they were just thinking, you know, 14 was their favorite number, so they just made some arbitrary scale from 0 to 14. No, the values on a pH scale correspond to an actual value. Now you guys think about it, if the pH scale is what we use to measure acidity, what do you guys think these numbers 0 to 14 might possibly correspond to? I'm hoping you guys would remember from our first lesson, you remember we were saying that what is it that makes acids acids? It's the presence of H plus ions. You guys remember when I put it in brackets, so you guys rewrite this and then show these values here. This is the H plus ion concentration. And so you guys can see, kind of see the relationship. So if you guys see when it's 10 to the negative 0, you guys know what 10 to the here, let's see. 10 to the 0 power would be 1, right? Anything to the 0 power would be 1. So that would have a concentration of 1 molar, okay? Now you guys look, 10 to the negative 1. You guys see, if you have a hydrogen ion concentration of 10 to the negative 1 in a solution, that's going to correspond with a pH of 1. And you guys see 10 to the negative 1. You guys remember how you guys can write it? Remember that's just 1 over 10 to the 1. 1 over 10 to the 1 is 1/10. And how do you write 1/10? You can write it as 0.1. You guys remember we were saying your stomach acid has about a 0.1 molar hydrogen ion concentration. 10 to the negative 2 is 1 over 10 to the 2, which is 1 over 10 to the 2 is 1/100th, and that would be 0.01. Look at 10 to the negative 3. That's 1 over 10 to the 3rd, which is 1 over 3 powers of 10, which is 1 over 1,000, which you write as 0.001. Now you guys see how these different, you guys, the pH scale is called a logarithmic scale. You notice how each pH unit corresponds to a power of 10, right? In each power of 10, you move over the decimal. So just realize that. So basically what we're doing is taking a wide range of concentrations, extreme, because you guys can imagine, you guys get the idea, and then this would be 0.001, this is 0.0001, such a wide range, and what we've done is condensed it using a logarithmic scale such that the differences just differ by 14 units. Okay, so the main thing I want you guys to recognize is the pH scale comes from actual values, and it's the actual values of the H plus ion concentration in solution. So once again, the greater the H plus ion concentration, you guys look, when you guys read 1 is greater than 0.1, which is greater than 0.01, the greater the hydrogen ion concentration, the more acidic. The lower the hydrogen ion concentration, the less acidic, or you would say the more basic. Okay. To go with this, I'm going to go back to, here I'm going to give you guys, here is how you actually calculate the pH. The pH is really simple. The pH, to calculate the pH of your solution, you guys remember the pH value corresponds directly to the H plus concentration, and it's a logarithmic scale. It's negative log of the hydrogen ion concentration. Okay, so when you guys are doing this, basically if you know the hydrogen ion concentration of your solution, you plug it into this equation and you will get the pH. So for example, if let's say my hydrogen ion concentration is 1 times 10 to the negative 3, so what, to get the pH of it, I'm going to just go negative log of 1 times 10 to the negative 3. And this is going to be, you're going to find this is really easy. So this is how you plug it in. I go 1, and I know you remember what we do to get times 10 to something? You go EXP, or you have an EE button on your calculator. In fact, I probably should do that. No, here, let me show that right over here. Okay, so I'm gonna go, hopefully you guys can see this. So I'm gonna go 1. Notice I'm gonna press the EXP button, or you might have an EE button. And then notice up there it's negative 3. So I'm gonna go, I put a 3, and then I change the sign. I see I have a positive and negative sign. I change it. And so I know it looks like it's 1 to the negative 3, but it's actually 1 times 10 to the negative 3. And then you know all I have to do is I just press this log button. See that log button? I press the log button, and now notice it says negative 3, but you guys notice it's a negative log, so I have to change the sign. So I just change the sign, and it's a positive 3. You guys see it's really easy. And you guys can see that right here. You guys see when it's 1 times 10 to the negative 3, the pH is 3. So somebody might say, well, why do I even need a calculator? Isn't it just the opposite sign of the exponent? Yeah, but what if your H plus concentration was 2.5 times 10 to the negative 4? You guys see it's going to be different when the value in front is different than 1. So what would I do? I would just get the negative log. To get this, I go pH is equal to the negative log of 2.5 times 10 to the negative 4. So once again, how do I plug that in? I'm going to go 2.5. Remember what I do? I go EXP, or EE, EXP. And then I'm going to go, I put 4, and I change the sign after. Your calculator, you might put the sign in before your number. I don't know how your calculator works. And then you guys, it's really easy. I just press the log button, and then I just change the sign. And you see what I get? I get 3.6. Since I only have 2 digits here, I'm going to just do the 2 digits here. And so my pH is 3.6. All right? Okay. Guys, I want to go back to our original thing here. Again, I'm going to have a question for you guys. Okay, let's look at our, okay. First of all, I'd ask, okay, you guys, what is more acidic? Let's say lemons or bananas. What are more acidic? And you guys should be able to answer. Well, obviously, lemons with a pH of 2, bananas have a pH of 5. The lower the pH, the more acidic. Lemons are more acidic. My next question is, how much more acidic are lemons than bananas? How much more acidic are lemons than bananas? And you guys look, the lemons have a pH of 2, bananas have a pH of 5. You would not say, oh, right? You guys see how there's a difference of 3? I can see where somebody would say, you guys got to remember, the pH scale is a logarithmic scale, and you guys remember each pH value corresponds to a factor of 10. That's how a logarithmic scale works. So how much more acidic? So if each pH scale corresponds to a factor of 10, I know what some people might say. They're like, oh, well, if it's a 2 to a 5, that's 3. So they go 3 times 10. They would say lemons are 30 times more acidic than bananas. No, they're not. I want you guys to think again. It's each one of these corresponds to a power of 10, or a factor of 10. So what's 3 factors of 10? You don't go 3 times 10, you go 10 to the third. So it's 10 times 10 times 10. What does that equal? 1,000. You guys, lemons are 1,000 times more acidic than bananas. Now you guys can imagine, what if I try to compare lemons with soap? Lemons with soap, look, pH of 2, pH of 10, that's 8 factors of 10. That's 10 to the 8th. You know how you do that? You go 1 and then you follow it by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And you guys, how much times more are lemons than soap? They're 100 million times more acidic are lemons than is soap. You guys see how a logarithmic scale works? You guys see how there's such a huge variation if we were to look at it from, you know, a standard perspective? But we take a huge range like this. Right now, imagine if we were comparing stomach acid with oven cleaner. Huge range. But by using a logarithmic scale, we've kind of shortened that to a range that just ranges from 0 to 14. All right, guys, that's all I got for you today. Until next time, we'll see you.